Air is heated by steam, which passes through tubes in a heat exchanger. Steam enters the heat exchanger at 30 psia and 400 degrees Fahrenheit at a rate of 15 pounds mass per minute and exits at 25 psia and 212 degrees Fahrenheit. Air enters at 14.7 psia and 80 degrees Fahrenheit and exits at 130 degrees Fahrenheit. Find the volumetric flow rate of the air at the inlet. Well, we begin this problem with an appropriate illustration. So here we have a heat exchanger. So let's just show this as the boundary of the heat exchanger. And we've got two streams. We have an air stream that comes in at point 1 and then leaves at point 2. And we have a water or steam stream that comes in at point 3 and leaves at point 4. So this is our water stream. Now we're given a variety of information. It tells us that the steam enters at a particular pressure and temperature. So P3 is 30 psia and T3 is 400 degrees Fahrenheit. We're also given a mass flow rate. So the mass flow rate, now this is a steady flow process, so this would be the same for the steam at the inlet as well as at the exit. That is 3 and 4 are the same mass flow rates. So we'll just put S for steam. So m dot steam is 15 pounds per minute. Or if we divide it by 60, we get 0.25 pounds per second, which would be the appropriate units for this type of problem. And then we're also given exit conditions. So P4 is 25 psia and T4 is 212 degrees Fahrenheit. With regards to the air, we're told that the air enters at standard atmospheric pressure, 14.7 psia, and at a temperature of 80 degrees Fahrenheit. And we're also given that the air exits at a higher temperature of 130 degrees Fahrenheit. And what we've been asked to find in this problem statement then is the volumetric flow rate of the air at the inlet. So V dot 1 is our one and only unknown for this particular problem. Now, for this problem, our first law equation is for a multi-stream steady flow process. So in that case, we have Q dot minus W dot equals, and then here we have a summation over all exit streams of m dot exit, and then multiplied by the enthalpy of the exit plus the kinetic energy change plus the potential energy change at the exit, and then subtract from this the sum over all inlet streams of the mass flow rate at the inlet times the enthalpy at the inlet plus the inlet kinetic energy change plus potential energy change. Now, in this particular problem, we have to make several assumptions. First of all, heat exchangers are generally very well insulated devices. I mean, you don't want to lose heat into the surroundings. You're trying to transfer heat from one device to the other. So in this case, Q is going to be assumed to equal 0. Keep in mind that this heat transfer term is only heat transfer that crosses the boundary of our system. The air and the water are both inside the system. So yes, heat is being transferred between the two fluids, but there's still assumed to be no heat transfer into the surroundings. Additionally, there's no mechanical devices, moving devices associated with this, so there's no work or power. So the W dot term is going to become 0. And then additionally, we're given absolutely nothing about the geometry. We don't know the diameter of the pipe at the inlet or the exit, neither for the airstream nor for the steam stream. So our only choice is to just assume that there's no kinetic energy change and that there's no potential energy change. Again, we know nothing about the height change of either the fluids, so we have no choice but to just neglect those two terms. So now let's then just rewrite our first law equation. In this particular case, everything has gone to 0. All that we're left with is 0 equals the summation overall exit streams of m dot EHE minus the summation overall inlet streams of m dot IHI. So now let's go ahead and plug in the appropriate numbers. So we have 0 equals, and then we have points 2 and 4 at the exit. So 2 is air, so why don't we just write m dot air H2, and then we add to that the mass flow to the steam times H4. And then on the inlet side, we have points 1 and 3. So for the air, we have m dot air H1, and then plus m dot steam H3. Now let's just rearrange this equation just a little bit to put the air streams and the steam streams together. So we have m dot air H2 minus H1, and then plus m dot steam H4 minus H3, and this equals 0. So this is our equation for the first law. Now, ultimately, we're trying to find the volumetric flow rate of the air. Let's keep in mind that there's a relationship between volumetric flow rate and mass flow rate. If we're trying to find the volumetric flow rate of the air at the inlet, then that's just the mass flow to the air times the specific volume of the air at the inlet. Now, we're given inlet conditions for the air. We have both pressure and temperature, so we'll be able to use the ideal gas equation of state, PV equals RT, or V equals RT over P. This is going to be the gas constant for air and the temperature and pressure of the air at the inlet. So this is going to allow us to find the specific volume at 1. And then our solution to the first law equation above is going to allow us to find our one and only unknown, which is the mass flow rate of the air. We then multiply the air mass flow rate times the specific volume, and that'll give me the volumetric flow rate. Now, if we look at the property data that's been given to us, and we look at the conditions for the steam, we have both temperature and pressure, and therefore we should be able to go into our property tables and find the enthalpy at point 3 and at point 4. So that data is all known. With regards to the air stream, we would assume that air is an ideal gas with constant specific heats, and as such, the enthalpy change for the air is just going to be Cp times the temperature change. Now, we do know the air temperature at both the inlet and at the exit. As such, we could take the average temperature and find Cp at that average temperature, and that would be more accurate than just using Cp at room temperature. So we'll use Cp average. As such, we're going to now rewrite our first law equation one more time. We have the mass flow rate of the air times Cp at the average temperature times T2 minus T1, and then plus the mass flow rate of the steam times H4 minus H3, and this equals 0. So let's then find the average temperature and find the value of Cp for air. We'll also find the enthalpy data we need for our steam, and then we should be able to go ahead and complete this problem pretty easily. So the average temperature for the air is just going to be T1 plus T2 divided by 2. So we're given T1 and T2 in this particular problem statement as 130 and 80. So we have 80 plus 130 divided by 2. So the average temperature then is just going to be 105 degrees Fahrenheit. Now, if we go into table A2 part B for air at the average temperature, then we'll find that Cp at that average temperature is 0.24 BTUs per pound mass per degree Rankine. Let's also go into our tables and find the property data for the steam. So at P3 and T3, here we have a superheated vapor, so that means we're going to have to go into table A6. So we go to the 30 psia subtable, we read down to the 400 degree Fahrenheit line. Actually, this is table A6E. And we find that the enthalpy at point 3 is 1237.9 BTUs per pound mass. We're also told that at point 4, we have a pressure of 25 psia and a temperature of 212 degrees Fahrenheit. Now, it turns out in this particular case that this is actually a compressed liquid. We would note that at 212 degrees Fahrenheit, the saturation pressure, as we all know, is going to be 14.7 psia. These are standard atmospheric conditions. However, our given conditions at point 4 are for a pressure greater than 14.7. So this clearly is going to be a compressed liquid. So whenever we have a compressed liquid, we either use the compressed liquid tables, but the compressed liquid tables provided in our textbook are very poor, and we don't have an entry at this low of a pressure, so our only choice for compressed liquid is to make the usual assumption, which is that it's approximately equal to that of the saturated liquid, HF, at the same temperature, not pressure, at the same temperature. So we're going to actually have to go then into our compressed liquid temperature table, which is table A4E, at the appropriate 212 degrees Fahrenheit, and we would find that the enthalpy is 180.21 BTUs per pound mass. So now let's then go ahead and complete this problem. We'll take our first law equation and just continue down here. So we have the mass flow rate of the air, which is our unknown. So m dot A. CP average is 0.24 BTUs per pound mass per degree Rankine. The temperature difference in Fahrenheit is the same as the temperature difference in Rankine, so we don't really need to convert from one set of units into the other. So we have 130 minus 80, and we'll just put Rankine. We add to this the steam mass flow rate, which we have as 0.25 pounds mass per second, and then multiplied by the enthalpy change, so 180.21 minus 1237.9 BTUs per pound mass equals 0. And now we just solve for our unknown, which is the air mass flow rate, and we get 22.04 pounds mass per second. Now, the only thing left here is to find our specific volume at the inlet for the air at point 1. If we go into table A1 or A2, E, we'll find that the gas constant for air is going to be 0.3704. And the units here are going to be psia foot cubed per pound mass degree R. Actually, if you look in this table, you'll see that there's 2 columns of data with 2 different sets of units. We're going to use this particular set of units simply because it'll make it easier in the end to cancel out my units. So that's the value of R that I'm going to use. Now we have our ideal gas equation. So again, V1 is RT1 over P1. Let's plug in the numbers. So 0.3704 psia foot cubed per pound mass degree R. The temperature at 1, well, we're given that as 80 degrees Fahrenheit. Certainly we're going to have to add 460 so that we get 540 degrees Rankine. The pressure at 1 was given as 14.7 psia. In fact, now you can see that the PSIA units are going to cancel. The only units we have left are cubic feet per pound mass, which is exactly what it should be. So we get 13.61 with the appropriate cubic feet per pound mass units. And now that we have a specific volume, now we find our volumetric flow rate. So V dot 1 is just going to be the mass flow rate of the air times specific volume at 1. Plug in the numbers above, and we get 300 cubic feet per second.